it goes. So in symmetric key cryptography, one of the key elements for this to work is that you have to have shared key between the both parties. So parties that want to do secure exchange of messages, they must use the same key. Otherwise, this will not work. So the whole security relies on secure transmission and storage of the key. The whole security relies on this. The key is top secret. You have to take care of it if you want to transmit it or if you want to store it. The challenge of symmetric cryptography is how can you establish a shared key with somebody you don't know or you haven't met before. We all first agree we cannot send the key through the communication channel, yes? Because the Eve or the attacker will have the key, and it's like defeating the whole purpose of encryption.
Could they be pre-installed in each machine or something?
It could be embedded in the application, yes. It could be embedded in the application. Hopefully they cannot reverse engineer it. Or you can do it offline. You can call the person or meet with them offline and agree on the key. Or agree on a password and generate a key based on the password. Sorry? Yes, through offline. Like offline, you meet them in the Aspire Park or you meet them in Villaggio and exchange the key. Or you go and travel to them once every few years or once in a lifetime and you share the key. Yeah, offline, you do it offline. You have a shared key, that's it. You have now secure communication over insecure channel. Remember, from the beginning we said this, that these two individuals, Alice and Bob, are exchanging messages through insecure shared channel. That's why we need to encrypt and decrypt, but we need to have the key. So sharing the key it's very challenging. We have to really find a way to exchange the key without the attacker knowing about it. Doing it offline is not, it could be for once off, but it's not scalable. You know, we access so many services over the internet. You cannot do it every time you want to communicate with Amazon. You have to call them, let's establish a key, and then use the key to place your order or put your payment. It's so unscalable. It cannot scale. Every time I want to talk to QNB, I have to go to the branch, please give me a key and get the key, scratch it, go and type it in and use it to encrypt it. You see, offline it's not an option. Online, if I put the key through the channel, the Eve will get it. And by the way, Eve could be any of these guys. It could be the internet provider, could be government, could be anyone using the same unencrypted network. A Wi-Fi network on the same place. If it's not using encryption, all the messages are plain text. They can see it. Anybody on the same network can see your messages. If we are using a shared switch or a router and we all connected through that, everyone else can type in and see the messages. So you need to be very careful here. Eve could be all these possible people. So picking a key and sending it, definitely not an option because Eve will get it. Doing it offline, kind of okay if we're doing it once off. If there is some spy and there is an agency that they work with, no problem. They will maybe meet once on a phone call and get the key and send it. It's fine. But if you are using it in the internet, where you access hundreds, maybe thousands of services, this is not an option. Yes? So we had to wait until 1976 for these two cryptography wizards, Whitfield Diffie and Martin Hellman. These two guys, they really changed the way cryptography works by inventing this protocol for key exchange. Although they call it a key exchange, but in reality, it could be called key agreement protocol. We use some protocol, we exchange a couple of messages, and we establish a shared key without actually sharing the actual key. We will see this. And this is a revolutionary idea. This is the breakthrough. It's a major shift. And this was the kind of the stepping stone for asymmetric cryptography that will come later. In here, we're still talking about symmetric. Symmetric cryptography, this protocol only helps us to do what? Agree on a shared key without sharing it in plain text through this insecure channel and without doing it offline. Yes? And once we establish the key, then what we do with the key? Use it to encrypt and decrypt using any algorithm, DAS, AES, or any other algorithm. Okay, so here is these are the two guys that invented this. And in 1976, in 2015, they were awarded with the Turing Award, which is an ACM, Association for Computing Machinery. It's a $1 million award, similar to, this is the CS Nobel Prize. Using colors. Explain the concept using colors, and then we will replace colors with the actual mathematics to do this, to show how this protocol works. Super simple. Have a look at this. The goal here is that Alice and Bob, they want to agree on a secret color that Eve should not be able to know. Yeah? So what they do first, they first agree on a shared color, public color. Eve will know about it, no problem whatsoever. So everybody starts with, both of them start with, which color we took? Yellow. And then each party will pick up another color, which will be a secret color. So we have one shared color, and each of them will have the secret color. So Alice will take red, and Bob will take blue. What do you think they will do with these colors?
Mix them together.
Mix them, thank you very much. So they will mix these colors. So now, yellow plus orange plus red gives you what? Orange. Okay? And yellow plus blue gives you green. What do you think they will do with this mixed color? They will exchange this mixed color. Have a look. They will exchange this mixed color. Now, of course, Eve will get a copy of this because they are using shared channel. No problem. They get, the attacker will get a copy as well. Now, what's the next step? So what they will do, they will mix the mixed color they receive from the other party with their secret color. So orange plus blue will give you what? Brown. Now, what Alice will do? She will do the same thing. She will mix the green she received from Bob with her secret color red. It will produce exactly the same color, brown. Okay? Eve will be able to do this? Will Eve be able to produce this brown color? Brown shared color? No way. Because even though she has these three, she mixes them. There's no way she can produce this color. Okay, so now let me just show you this in a kind of realistic way. There is a little website that I discovered. You see here, let me just create 2 copies of this. Tricolors.com. So here is Alice. So there is Alice. They both started with yellow, yes? And then what did Alice, which color did she choose? Red. So red plus yellow will give us what? Orange. So here is the orange that Alice produced. What she will do with this orange? Send it to Bob. Now Bob on his side, what color he picked? Blue. Blue plus yellow is green. Here's the green. So what he will do with the green? Give it to Alice. So Bob will have this, and Alice, she will have this, the green one, yes? Now, what Bob will do with this orange color he received from Alice? He will add his secret color. What was his secret color? Blue. If we add blue, we get the brown. Now, Alice, she receives the green. What was her secret color? The secret color for Alice, the red. So we add the red, exactly the same color. They arrive, both of them arrive to the same color. Okay, so let me summarize it. You get the idea, yes? So basically, they start with a shared color. So they start with a shared color, public, everybody, like even the Eve will know about it. They choose each of them secret color, and they mix the shared color with their secret. Then the mix, they exchange the mix, and then they add the secret color to the mix, and they will both arrive to the common shared color. Is this clear? Yes, please.
What if we took the orange color or the one they sent both?
Yes, the orange and the green in this scenario.
Yeah. What if we took one of them and just reverse it with and get the original color?
Oh, this is very good. This is very good question. But have a look at this. In real life, it is super easy to mix colors. But given a color, can you reverse it? Can you unmix it and produce the original separate two colors? It is impossible. Is clear? This is the key idea of this protocol, is that we have a function that is easy to compute, but very hard or almost impossible to undo or to reverse. That is the key idea. Now, of course, this is the analogy. All this stuff is an analogy to bring the idea closer to your mind. But the actual protocol uses mathematics to do this, and quite simple math to do this. So here is the algorithm. This is again taken from Wikipedia. So what we do here, we have Alice and Bob. They will first agree on two prime numbers. In reality, they will be large prime numbers. You know prime numbers? A number that can only be divisible by itself or by one, not any other number. Okay, they will pick up large prime numbers, G and P. In this case, I picked 23, and G is 5. Now, what Alice will do, she will compute A. A is G to the power of A. A is a random number that Alice has picked up. She selected a random number, secret number, and she computed this big A, which is G to the power of A mod P. And here, with A equals 6, she will do the computation and produce this value 8. Now, what she will do with this 8? Send it to Bob. Thank you very much. So what Bob will do, he will do exactly the same thing. He will pick up a random number B and compute the big B, which is G to the power of B mod P. If he chooses the value 15, so this will produce this big number mod 23, gives us 19. What he will do with this 19? Send it to Alice. So far here, similar to the mixing of colors. We start with, let's say, a common yellow color. Here, Alice selected the red color and Bob selected the blue color, for example. Instead of doing with colors, we are doing here with mathematics. In particular, this is modulus exponentiation. Very simple formula. We take a base, which is often called generator, G, denoted as G. We do exponents of a secret value, mod P. G and P are public. Public means even the attacker will know them. We send them in plain text through the channel. Yes? And then these intermediary values we compute in each party computes, they will exchange them. Now, the next step, so Alice, she will take the value received from Bob, and she will do exponent, do the power of, make it to the power of the secret's value. So B power of A mod P. She will produce this value, shared value S. And surprise, surprise, this value will be 2 in this case. And Bob will do exactly the same. They will receive the value A from Alice to the power of their secret number, in this case B. And then basically they will produce exactly the same value, 2. So using this protocol, we are now being able to establish a shared key without actually sending the key. We are establishing this through a protocol. Remember, in cryptography, we have 3 major subcategories. It was cryptography, cryptoanalysis, and protocols. One of the protocols, very important protocol in cryptography, is Diffie Hellman. Diffie Hellman protocol. What we use this protocol for? Exchange the key or agree on a shared key without actually transmitting the key. Yeah. So let me summarize this. Here is, we do this once off. We agree on 2 values, G and P. Then each party will generate a random number, A and B. In this case, Alice picked 6 and Bob picked 15. We compute A and B. Alice will compute A using G to the power of A modulus P. And Bob will do the same. B equal G to the power of B mod P. They will exchange these values. Once they receive these values, they will do the same thing. Take the value received to the power of the secret value, mod P. Same thing here. The value received to the power of the secret value, mod P. And they will arrive to the exact same shared key. Yeah, have a look at this. If you look here carefully, this is what Alice received from Bob, is G to the power of B. What she did, she took that and did to the power of A. And Bob, this is what he did. He received J to the power of A, and what he did with that, make it to the power of B. If you look carefully, this can be swapped. Mathematically, J to the power of B to the power of A is the same as J to the power of A to the power of B. Mathematically, this is equivalent. These are equal. That's why we arrive at the same shared key.
Still in use?
Sorry?
Still in use this
Of course, this algorithm is very, very critical. It's used billions of people on the internet. There are 2 major algorithms that are heavily used in real life, Diffie-Hellman and RSA. That's what we will see later on. But just to tell you, we are not throwing the symmetric key away. Here, what are we doing?
What are the same?
Just establish the key, then use the symmetric encryption to encrypt and decrypt. Yes? Here, this protocol is only for key exchange. That's it. Just for key exchange. Heavily used, widely used, very, very important algorithm. Very important discovery that really changed how crypto works. Okay, in real life, A, B, and P, especially A and B, are huge prime numbers, hundreds of digits long. They must be hundreds of digits long, otherwise this will not work. You will see why shortly. So the idea, remember in the colors, we had an easy a one-way function, which means it's easy to compute on one way, but impossible or very hard to reverse. Remember the colors? If we have 2 colors, mixing them is super easy, but separating them after mixing, it's very hard, almost impossible. Same thing here. Take a look at this. So what Alice and Bob are doing, modular exponentiation. So all they do, the blue values are public. So we take these blue values, we take G to the power of the secret value, modulus P. This is super easy to compute. Now, if I know all the values here except the exponent, which means if I want to break the system and find out the exponent, the problem becomes like this. Given 2 and given the 19 and 23, what was the component used, the exponent used to produce 2? This problem in mathematics is known as discrete logarithmic problem. This problem is so hard, there is no efficient algorithm out there. So the security of Diffie-Hellman relies on what?
It cannot be reverse engineered.
Yes, we cannot work out the exponent. So basically, in math, if you take advanced math, this problem, by the way, if you want to get a Nobel Prize, just solve this problem. There is no efficient algorithm to do it. The only way to do it is trial and error, which means try 0, 1, 2, 3, and keep trying until you arrive to the number. And by the way, if you take the secret number, hundreds of digits long, then that will take you years to do so. Yeah. The only way to do it, in other words, is brute force, by trial and error. There's no other way to do it. There's no other efficient way to do it. Okay? And if you take a large number, that will take very, very long time, even if you have very strong like if you have powerful computing capabilities. It will still take you a long time. So that's what makes Diffie-Hellman work in practice, is by using a large secret numbers, A and B, taken by both parties. The difficulty of solving this discrete logarithmic problem is the secret of this, why Diffie-Hellman really works. Which, at the core of this Diffie-Hellman algorithm is this one-way function. What it means here, have a look. If you look a little bit more deeper into this protocol, so you can think of it as Alice has a secret key A, and Bob has a secret key B. So what they do here, they will shield it. They will take the key and protect it, make it kind of invisible. The key is there, but it is shielded. How do we shield the key? How do we protect the key before we send it to the other side? By taking it through this simple one-way function. This is my key, which is my secret number. I do this simple modulo exponentiation. I'll take the g to the power of a mod p. This g and p are public. And this will produce another key, which is nothing but my original key, shielded, protected. Nobody can reverse it. Why they cannot reverse it? Because this is a one-way function. Easy to compute, very, very hard to break, very hard to undo or to reverse. That's basically the core idea of this Diffie-Hellman. So you see here, if I give the inputs G and A, give it to this formula, super easy. I can just compute it and produce A. But here, given A, which is 2, given this 23 and 19, almost impossible to break this. Sorry, it's very hard. Not impossible, but it will take a very long time. Except using trial and error, it will take you a very long time to really remove the shield and compute this exponent that was used to produce. So here, if I just put question mark here and do equal to, of course, with small numbers, you can work it out very quickly. But for large numbers, hundreds of digits long, it will take you very, very long to work out what was the exponent used. Just to summarize, the whole idea behind Diffie-Hellman is this one-way function. Basically, they use math and they find one function, in this case, modular exponentiation. It is very easy to compute, but very hard to reverse. That's basically the key idea. And this key idea has revolutionized the way we do cryptography. So RSA or other more advanced asymmetric cryptography that we will be starting to cover next class rely on this idea that we have one mathematical function, easy to compute, but very hard and time consuming to reverse.